Okay, guys, so for today, we're going to be talking about acids and bases. We're going to talk about their characteristics, the couple of definitions that are available for acids and bases, and then we're going to talk about the naming of acids, which truly depends on whether the acid has an oxygen or not. So, jumping into the next thing, let's start off with characteristics. So acids and bases do have a couple different characteristics, and I've just highlighted a few. So acids are usually sour and bases are usually bitter. So an example of an acid is things that have citrus, like your citrusy fruits, things like lemon, oranges, etc. So these things, do contain citric acid, and we already know that those types of things are sour to the taste. And then we also have example of bases, things like baking soda, soap. These are things that we can't really taste, but if you do have the misfortune of tasting soap or like cleaning supplies, you're going to notice that they are very bitter to the taste. And then in terms of reactivity, both acids and bases do tend to cause a bit of damage. The terms we use to describe the damage caused by acids and bases are different. Acids are corrosive and bases are caustic. So corrosive things usually cause damage to the skin. Have you ever heard of a metal corroding due to acid attack? Then usually in that case, it's due to it being corrosive. And then in terms of bases, we just use the term caustic. And then when we're talking about pH, we know that pH is on a scale from 0 to 14, with 14 being the most basic, 0 being the most acidic, and then 7 is neutral. So from 0 to 7 is acidic, and then from 7 to 14, that is basic. So this area over here is for acids, and then this one over here is for bases. So if you see something that has a high pH, then that suggests that it's basic. Something with a low pH like hydrochloric acid or stomach acid, then those ones are usually for acidic. And then in terms of conductivity, both acids and bases are able to conduct electricity, because electricity is all about flow of current. So electricity, that is flow of charge. So because both acids and bases are able to ionize to make ions, these ions can move, and the movement of the ions cause electricity. And then in terms of litmus paper and phenolphthalein, these things are things that are able to identify how acidic or how basic something is. So litmus paper, for acids, blue litmus paper changes to red in the presence of an acid, and then red litmus paper changes to blue in the presence of a base. And then phenolphthalein is the name given to an indicator that is able to keep track of how acidic or how basic something is. So phenolphthalein is usually colorless in the presence of an acid. However, it does go pink in the presence of a base. And then acids and bases are usually able to take part in something called a neutralization reaction. This is when an acid reacts with a base and it produces salt and water. An example of this is when you have, let's say you have hydrochloric acid reacting with sodium hydroxide. What happens is that the H here adds up with the OH here, and then the Cl adds up with the Na. So that ends up producing sodium chloride, which is a salt, plus H2O. The key here is that water is being formed, and then everything else combines together to form a salt. We have a couple of different definitions for acids and bases. One of the definitions is the Arrhenius definition. This one is literally talking about what is produced in the presence of water. So for acid, if you add water to an acid, the acid will produce H plus or a proton when in water. So H plus is usually also called a proton. And so what happens is that in the presence of water, HCl would break down to produce H plus Cl minus. Some people write it like this: if HCl is added to water, then you end up producing H3O plus, which is a hydronium ion, plus Cl minus. The hydronium ion, which is H3O plus, is interchangeable with H plus. So these two are very similar to one another. And then you have examples of acids that are called polyprotic. So this is a polyprotic acid. We call it polyprotic because it produces multiple protons or multiple hydrogen ions. So this H2SO4, which is sulfuric acids, end up producing 2H plus SO4 2 minus. Now is a good time to talk about the components of an acid. So your basic acid has the format HA. H is talking about the hydrogen part, and then the A is the anion. So the anion is the negative ion that combines with the H plus. So examples of anions include Cl minus. You could also have SO4 2 minus, and it could get more complicated. But these are the negatively charged ions that combine with the H plus to make the acid. And then talking about the Arrhenius definition of a base, usually Arrhenius bases produce hydroxides in the presence of water. So it breaks down to produce sodium ion, this is sodium hydroxide, by the way, and then it produces the hydroxide ion as well. And then you also have cases where in a single base molecule or in a single base, you have multiple hydroxide ions. So this calcium hydroxide would break down to produce calcium 2 plus 2 hydroxides. Okay, so we also have the Bronsted-Lowry definition. The Bronsted-Lowry definition is just talking about transfer of hydrogen. So the Bronsted-Lowry acid typically donates a hydrogen, and then the Bronsted-Lowry base usually also accepts a hydrogen. So let's look at the acid, hydrochloric acid. If it reacts with water, we've already done this reaction before, it produces hydronium ion H3O plus and then Cl minus. So you're going to notice that this acid over here gave its H so that it can go and combine with water to make the hydronium ion and then the chloride ion on the product side. So this is an example of a Bronsted-Lowry acid because it is donating a H and it's given it to a different species, and you see the product over here. And then looking at the definition for bases, bases are what are accepting the hydrogen ion. So that means in the case of ammonia, you can have ammonia reacting with water, and then that produces NH4 plus, which is the ammonium ion, and then you can also get an OH minus. So we're going to notice that one of the H's in H2O went over to ammonia, and ammonia took that H and turned it into the ammonium ion, and all that was left behind was the hydroxide ion. So the Bronsted-Lowry acid and base definition, that is only looking at, how the H pluses transfer, which is good because now we can look at how unique water is, because we can actually say that water is amphoteric. Water is amphoteric because it acts as both an acid and both a base. It acts as both an acid and a base because in the case of the acid, it can donate a H plus, and if it acts as a base, it can accept a H plus. So in the case of looking at the Bronsted-Lowry acid, HCl reacted with H2O. And so H2O did gain a hydrogen and became H3O plus. So in this case, we're seeing how HCl is an acid, and then H2O was a base in this case. And so what happens is that HCl turns into Cl minus, and then H2O turns into H3O plus. And this is all related to losing a H plus on the end of HCl and then gaining a H plus on the end of H2O. So this HCl became Cl minus. So HCl is an acid, and we can call Cl minus the conjugate base. This is a conjugate base because if we imagined that this reaction were to happen in this direction, not that this is the case, but if we were to imagine it going in the opposite direction, then Cl minus would have gained the H back. And we know that Cl minus is a base because it can gain a hydrogen, without any issue. So that's just by the way. And then H2O was the base here. And so it becomes H3O plus, which we're going to call the conjugate acid. Conjugate acid. So the relationship between H2O and H3O plus was the gain of a H plus, the gain of a proton. So acid on one side becomes conjugate base on the other side. Base on one side becomes conjugate acid on the other side. So we see H2O acting as a base in this instance. But then what about H2O acting as an acid, which we see over here? When H2O acts as an acid, you have ammonia reacting with H2O, and so H2O donates a H plus to NH3, which is ammonia, and it becomes NH4. So there is a relationship between NH3 and NH4, and then there is a relationship between H2O and OH minus on the other side. Still related to H plus. So NH3 becomes NH4 plus by gaining a proton, by gaining a hydrogen ion, and then H2O becomes OH minus by losing a hydrogen ion. So NH3 gains a H plus, so that is the base in this case, and it's related to its conjugate acid. I'm just going to abbreviate that as Ca on this side. And then H2O is an acid in this case, and it's related to the conjugate base, the hydroxide ion on the other side. So we do see how water can act as both an acid and a base. So we would call that amphoteric. And we've also done a bit of review on acids and conjugate bases, as well as bases and conjugate acids. And then we have the third definition of acids and bases, which we can call the Lewis definition. The Lewis definition is only focused on movement of electron pairs. All right, so what does that mean? Acids accept electron pairs, Lewis acids accept electron pairs, and Lewis bases donate electron pairs. How I always like to remember it is A for A. So Lewis acid accepts electron pairs. Okay, so, and then of course Lewis bases donate electron pairs. So let's look at this typical reaction happening here. You have ammonia and it's reacting with boron trifluoride, which is BF3, and that combines together to make this compound over here. So ammonia in this case is a base. So I'm just going to write that it's a base because it's donating electron pairs to boron trifluoride. Let's think about this. So anytime we're trying to find out, what makes a compound or an element stable, we usually want for a typical atom to have 8 electrons surrounding it. But right now, boron trifluoride only has 6 electrons surrounding it. So 2 electrons from this bond pair, 2 electrons from this bond pair, and 2 electrons from this bond pair. But now we're trying to get it to a stable octet. So we're trying to get it to a stable octet of 8. So we're going to want to gain 2 electrons or an electron pair. So an electron pair. And so that's why we can basically look at this reaction here, because ammonia which is the base in this case, has an extra lone pair it's willing to share. And so overall, ammonia will donate an electron pair to boron, and then boron, of course, is going to accept the electron pair, making it the acid in this case. And then you're going to end up with the new compound where both nitrogen and boron have a stable octet, but then boron has gained an electron pair more or less, and nitrogen has donated an electron pair partially. So now they're agreeing to share the electron pair. So that's the definition for Lewis acids and Lewis bases. So there's 3 different definitions we have looked at. And now let's talk about naming acids. So remember when I talked about how an acid has a basic formula of you have a hydrogen and then there is an anion. Doesn't really matter how many hydrogens you have. You can have 2 hydrogens, 3 hydrogens, or just 1 hydrogen. So X can be any number. And then you have the anion. So we would break down to produce however hydrogens you had plus the anion and whatever charge you had before. So X minus. An example would be if I have H2SO4. This is one of my favorite examples. You produce 2 hydrogens and then SO4, 2 minus, so that the charges complement and cancel each other out. So now let's talk about if you have an anion without oxygen. This is an anion where there is no oxygen at all. So this isn't an example, but we do have a couple of examples here, like HCl and HCN. In HCl, what's the anion? Giving you a couple seconds. Yes, so in that case, it's going to be Cl minus, that's the anion. And then in Cn, the anion here is Cn minus. So that's the anion here. So if we have acids that, don't have any oxygen, we can name the corresponding acid according to the anion name. So Cl minus, that is chloride. And Cn minus, that is cyanide ion. And so the root of these anions, in the case of chloride, the root is going to be chlor. And the case of cyanide, the root of the anion name is cyan. Okay, so we are in a situation where we have a formula for naming these compounds. The formula basically says you're going to name it according to this hydro, and then the anion root name, and then ic acid. So let's give it a try. So we have HCl. We can say it's hydro, and then the anion root is chlor. So we can put, I'll just change that to chlor, and then you can put ic after that. So it's hydrochloric acid. Just erase this over here. So yes, it's going to be hydrochloric acid. And then let's try another one. If you have HCN, then we can say the name is hydro anion root ic acid. Okay, let's give that one a try. So it's going to be hydro cyanic acid. And both these things are acids. And that's how you name it for anions that do not contain an oxygen. Now let's talk about anions that do contain an oxygen for naming of the acids. I have a little reference table. This is by no means an exhaustive list of all the anions in existence that contain oxygen. There's a lot more. For example, we don't even see oxalates. So this is just for practice. So if your anions that contain oxygen would usually have a suffix of ITE or ATE. So if it ends with IDE, there is no oxygen. So this IDE suffix means no oxygen. But then the other ones over here do have oxygen. So they end in ITE, like over here in hypochlorites, or they end in ATE, like in the case of bromates. So if it has a suffix of ITE, it means there is less oxygen, but there is still some oxygen in the compound. And then the suffix of ATE, that means more oxygen. Okay, and so hypo as a prefix means even less oxygen, and then per means even more oxygen. So let's look at examples. So looking at the chloride or the chloride line that contains both chlorine on its own and chlorine with oxygen, you can have chloride, and then if you add one oxygen, you get hypochlorites, and then you can get rid of the hypo and it will give you chlorites, which means there's one more oxygen, and then you're adding more oxygen, so you go from chloride to chlorates, and then add even more oxygen and you get perchlorate. The same thing goes for bromide to hypobromite to bromite to bromate to perbromate. Same thing goes for iodine. You have iodide, hypoiodide, which is, really low oxygen, but not no oxygen at all. And then you go into iodite, and then iodate, and then periodate. Sulfide. There is no hyposulfite or anything, but you do get a sulfite, and then a sulfate, and then a persulfate. Notice how the charges are all the same per line. So chloride is minus, ClO is still minus, ClO2 is minus, ClO3 minus, ClO4 minus. So the oxygen number is not really changing the charges for these oxygen containing anions. Even in the case of the sulfide line over here. The sulfide line, you are having a situation where everything is 2 minus all throughout, regardless of the number of oxygens that are present. Even for the iodide line as well, but not the case for nitrogen. Nitrogen, you get N3 minus, but then even comparing nitrites and nitrates, there's still -1 charges for these polyatomic anions. Okay, so we can name the anion following the rule that if the anion name ends with an 8, you can put the root name of that anion and then add ic acid. And then if the anion ends with ites, which means less oxygen, then you can change the acid name to us acid. Let's try it out. So let's say the anion involved in the acid is SO4 2 minus. If we check our chart, we're going to see that SO4 2 minus is sulfate. Sulfate. So that means that we're going to keep the roots. And if we want to name the corresponding acid to this, we're going to call it sulfuric acid. So the ic is going to be there because it was an 8 before for the anion. So H2SO4 is sulfuric acid. But then let's try the other rule where if the anion ends with an ite, you're going to change it into us acid. Okay, let's try it. Sulfite, which is SO3 2 minus. This is sulfite. The corresponding acid is going to be H2SO3. What is the name of this? So if it was sulfide, then the root of the anion is still going to be sulf, but then it was an ite for the anion, so I'm going to change it to us acid. So it's going to be sulfurous acid. Okay? Now, let me go in and erase a couple of these so we can try the hypo and per naming as well. The rule still remains the same. Let's say that the anion I'm dealing with is hypochlorite, like this. So this is hypochlorite. This is an ite acid, so it's going to become this is an ite anion, so it's going to become an us acid. So the root here is hypochlor. So if I want to name HClO, it's going to be hypochlorous acid. And then let's talk about the other instance here. So if I have, just picking a good one, ClO4 minus. So ClO4 minus, what is that? ClO4 minus, that is perchlorate. That's the name of the anion. The root here is perchlor, and then it's an 8 anion, so I'm going to change it into an ic acid. So HClO4, that would be perchloric acid. So I hope this makes sense, and I hope that this was helpful to you. I really wish you all the best, and if you have any questions, feel free to put them in the comment section. If there's any comments you'd like or any topics you'd like for us to cover, also mention it, and feel free to share this to your classmates as well.